All right. The definition, it says let f be defined on an interval I containing c. F of c is called a minimum of function f on that interval if f of c is less than or equal to all f of x values in that interval. F of c is a maximum of f on that interval if f of c is bigger than all the other f of x values. The minimum and maximum of a function on an interval are the extreme values, or extrema, of the function. Note, extremum is the singular of extrema. Extrema is the plural, extremum is a singular. The minimum and maximum of a function on an interval are also called the absolute minimum and absolute maximum, or global minimum and global maximum. So you can have, and we're going to do an exploration here that's in your textbook. So open your books to page 164 so you can see the picture. Okay, open your books. It says, a function does not necessarily have a minimum or a maximum on an interval. It depends on what's your interval. So on page 164, do you see there are three pink pictures? The first one says f is continuous on the closed interval from -1 to 2. That means when x is -1, it's included, and when x is +2, it's included. So there's a maximum at 2, 5, and there's a minimum at the vertex 0, 1. In letter B, if it's an open interval, there's no maximum. Do you see, as I'm getting closer and closer to y is 5, I never touch it. So I can get 4.9, 4.99, 4.999999999, and I never get there. So there's actually no maximum on that open interval. However, even though it's open, an open interval, I have a minimum. I have a lowest value over the whole curve. And then in C, it says, okay, G is not continuous, so there's a removable discontinuity. So there's a maximum, though, at the 2, 5, but do you see there's now no longer a minimum? And so what we mean by absolute or global is over the whole picture that they're giving us, is there a highest value than all the others? That's called an absolute or global maximum. If there's a lowest value, it's referred to as a global or absolute minimum. Okay. So Theorem 3.1 says the extreme value theorem. If f is continuous on a closed interval from a to b, then f has both a minimum and a maximum on the interval. We're going to do a little exploration here, and it says the extreme value theorem is an existence theorem like the IVT. What's IVT? Intermediate value theorem. It tells the existence of a minimum and maximum, but does not show how to find them. So what we're going to do is we're going to use our graphing calculator. So let's go ahead and put in our y screen in y sub 1. It's x squared minus 4x plus 5, and we want this on the closed interval from -1 to 3. So from -1, did you guys know you can press trace and -1 and it'll spit out what the y value is? Did you know you could do this on your calculator? Maybe you forgot. So I only want this from -1 to +3, so let's hit 3. So that's 3, 2. And then how can we locate that low point, that minimum? Second trace, and you do minimum. You don't guess what it is, okay? Don't guess, because you could get lucky, but then you could get unlucky. wrong thing? Uh-oh, it's going to give me an error.
2.
Sorry. I knew it. Yes, I knew. Okay, so here we go. Let me try this again.
So left bound, you want to go to the left.
Yes, that would be a good idea, wouldn't it? So I'm going to move to the left, move to the right, and it is at 2, 1. So let's make a little sketch here. At -1, it was up here at 10. At 2, here's 2, 1. And then wasn't it 3, 2? So we're only looking at this chunk, okay? Only this particular chunk. So we have a minimum at 2, 1, and there is a maximum, right? What y value is taller than all the other y values? The 10, and that was at -1, 10. Are these exact or approximate? These are exact. These were not approximations. Okay, so now in your y screen, go put number 2 in there. X cubed minus 2x squared minus 3x minus 2. And let's take a look at this graph. And again, I'm only interested in the piece from x is -1 to +3. So let's hit trace and do -1. So that's -1, -2. Let's do +3. That's 3, -2. And then go find that little dip. Okay, so it's really this piece here. So I'm getting a maximum at -0.535, -1.121. And I'm getting a minimum at 1.869, -8.065. And these are clearly approximate. Do you guys see how I got that?
How did you get the maximum?
Let me go back and show you. The maximum's right there,
I didn't know
right?
you were doing that piece too.
Well, it's from -1 to +3, so it went up a little bit from -1. It came up, yeah. So you have a little bit of a.
What was the minimum?
Let me go back.
Sorry.
No, you're fine. There it is. Okay, so when you are looking at the graph and you have a point that's higher than all the other points, it's referred to as a global or absolute maximum. If you have a y value that's lower than all the other points, it's referred to as a global or absolute minimum, okay? Because now we're going to move to relative extrema. Okay, does everybody have 2? All right, so now we're going to talk about relative extrema and critical numbers. It says, given the graph of f of x equals x cubed minus 3x squared, the function has a relative maximum at 0, 0, and a relative minimum at the point negative 4. What I want you to do is, let's go to our graphing calculator, and I'll put that back in a moment so you can keep filling in. But let's go put this in here. X cubed minus 3x squared. And we can graph it. This is on your paper. And so here's the 0, 0 right here. Okay, this is 0, 0, and here's your 2, negative 4. The reason why they're called relative is that it does shoot up to infinity, right? That isn't the highest point. And it shoots down to negative infinity, so it really isn't the lowest point. But informally, for a continuous function, you can think of a relative maximum as occurring on a hill. You have a little bit of hill where it came up and then went back down. Okay, think of driving. And a relative minimum as occurring in a valley. Such a hill and valley can occur in two ways. If the hill or valley is smooth and rounded, the graph has a horizontal tangent line. So think of it like this. There's a horizontal tangent line, right? Oh, okay, so now we're going to bring in our calculus. So far we haven't really done any calculus yet. So, and you could have it where, you know, the curve's going down, so you have your valley, but there's still a horizontal tangent line. Now, if the hill or valley is sharp and peaked, so let's think of our absolute value curve. Can't I have a relative minimum here? But there's not a horizontal tangent line. What happens at a corner?
Because it touches on. I know what I'm trying to say, but like I can't.
It's not differentiable.
It's, okay, great, I love that. Okay, at this minimum, f is not differentiable.
Gotcha.
So it says if the hill or valley is sharp and peaked, the graph represents a function that is not differentiable at the high point or low point. So what we're going to be looking for, okay, because now we're going to want to use calculus here to help us, is that you're either going to look for where is f prime of x equal to 0, or f prime of x does not exist. That's where you're going to get a valley or a hill, okay? This is really, really important. So the formal definition of relative extrema. Everybody have that? It says, if there is an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f. You can say that f has a relative maximum at C, comma, f of C. If there's an open interval containing C in which f of C is the minimum, then f of C is a relative minimum. Or you can say f has a relative minimum at C, comma, f of C. Relative maximum and relative minimum are sometimes called local maximum or local minimum. So let's pause here a moment because I'm giving you a lot of new vocabulary. You have global or absolute, and I think that should make sense. If you think of a global situation, that's over the whole thing. Absolute is over the whole thing. Relative or local is in a small location. Do you have a hill or a valley? Okay? All right, so, yeah, Olivia.
So for the absolute one or the global one, like when we graphed it, if we would have changed our window, there would have been endpoints. But on the relative one, it goes to infinity.
Right.
Okay.
Yes, exactly. So usually when you're getting global, they're giving you a closed where it's just from here to here.
Yeah.
And so here's what's interesting about global. I'm glad you asked. So if you're talking about global, I mean, I could have a hill here, but that's not my global max. It would be up here. Do you guys see that?
So it can be infinity.
Okay.
No.
That makes sense.
It can't.
That's in
Yeah, I mean, because you can't attain infinity. No, I'm saying that, say I bounded it here and here. Even though I have a hill, I can't say that it's not a global maximum. It's a relative maximum, but my global would be up here, even though it's not at a hill. Okay? Alright, so let's look at example 1. It says find the value of the derivative at each relative extremum. So in letter A, it says f of x equals 9 times the quantity x squared minus 3 over x cubed. So let's tidy up that numerator and make it 9x squared minus 27 over x cubed. And let's go graph it and find where there's any relative extrema. So let's go there. So in my numerator, I had 9x squared minus 27 divided by x cubed, right? Now this did say for x is greater than 0, right? So can you see there's some kind of maximum occurring here on this right side? Okay, so we're going to do second trace. We're going to go to maximum. And I'm going to try and do it the right way now. Okay, here we go.
What else you mean the left way?
Ha ha ha, yeah. And it's at x is 3, right? So there's a relative max at x equals 3, but it says find the value of the derivative at that x value. So I'm going to do the derivative, and I'm going to take low d high minus high d low over low low. So what's really nice is the whole rest of the year we're going to keep practicing the quotient rule, the chain rule, the product rule. We're going to keep working them because they're sub-concepts in what we're doing. So this is what? 18x to the 4th minus 27x to the 4th plus 81x squared.
Don't we have that up at the very top?
What?
Oh, we're just finding the
We're finding the derivative right now because it said plug it in for the x value of your relative.
Could you just plug it into the derivative on top?
The 3?
Killjoy. The very first thing we did.
Here?
Yeah.
That's not the derivative.
Oh, we just simplified it.
Yeah, I just simplified. That's not the derivative. Okay. So what I'm going to do is I'm going to factor out an x squared because this is kind of big to plug in yet, I think. So let's pull out, and I'm going to get negative 9x squared plus 81 over x to the 4th. Now plug in that x is 3. So negative 9 times 3 squared plus 81 over 3 to the 4th.
You get a 0.
Oh, what's that mean?
That is right.
There's a horizontal tangent line there, which there should be. Okay.
So is that like checking your work?
Yes, this is like just checking our work. Now, in letter B, you should know what this graph looks like, right? And so this is the parent function. So there's a relative minimum at x equals 0. Now there's a problem here because when you deal with absolute value, do you remember that, like, I can't, the way that it's written, I cannot find its derivative with an absolute value. Have you noticed we didn't really do derivatives with absolute value? However, we could do this. This is equal to x if x is greater than or equal to 0, but it's negative x when x is negative, right? So if this is f of x, I actually have to take both derivatives, okay? I have to take the derivative of the top line and the bottom line. And so the derivative is 1 when x is greater than or equal to 0, but it's negative 1 here, right? So f prime of x does not exist, but there's like a formal way for us to do it, okay? All right, now, the last one, f of x equals sine x from 0 to 2 pi. Now, that's an open interval, right? So let's make our little sketch. So here would be an open circle. Open circle. So you're not including them. So there's a relative maximum at x is pi over 4, and there's a relative minimum at x is 3 pi over 4, or excuse me, 3 pi over 2. So we want to find the derivative, and I want you to notice that we're not using any calculator here, that this would be fair game on the no calculator part. So what is f prime of x? If f of x is sine x, what's f prime of x? Cosine x. So we want to find f prime of pi over 2. So what's cosine pi over 2?
0.
0. And what's f prime of 3 pi over 2? Cosine 3 pi over 2. 0, right? You gotta review your unit circle, okay? And doesn't it make
0.
sense though? Because here's your derivatives, right here and here. They have horizontal tangent lines. So what I'm trying to emphasize here is where you have a relative extrema, the derivative there is either equal to 0 or it does not exist, okay? That's the big idea. So note, in example 1, at each relative extremum, the derivative is either 0 or does not exist. The x values at these special points are called critical numbers. You can fill in the blanks there. They're called critical numbers. Notice in the definition below that the critical number c has to be in the domain of f, but c does not have to be in the domain of f prime. So here's a definition of a critical number. Let f be defined at c. If f prime of c equals 0, or if f is not differentiable at c, then c is a critical number of f. Theorem 3.2 says, if f has a relative minimum or a relative maximum at x equals c, then c is a critical number of f. So critical numbers are where f prime of x equals 0 or f prime of x does not exist. I don't think I've said this enough yet. Alright, so finding extrema on a closed interval. Here's what you're going to do. You find the critical numbers of f, and in order to do that, that's where f prime of x equals 0 or does not exist. Evaluate it for f, and whichever is the least is the minimum, whichever is the greatest is the maximum. So let's actually do a problem. Let's look at example 2. If you want to find the critical numbers, you're going to find where is f prime of x equal to 0. So f prime of x is 12x cubed minus 12x squared. You guys, do not skip this step. Some of you jump to putting it equal to 0, and I know you're trying to do things as efficiently as possible. However, on the free response, sometimes they will give you a point if you wrote f prime, what f prime of x is. If you jump to 0 equals, you did not identify that this was f prime of x, and you received no points. So do you guys understand what I'm saying? Just put a little bit of effort in here and write it down. Then we're going to factor it out. and I pull out a 12x squared, so my critical numbers are 0 and 1. Now what you're going to do, and this is where students can sometimes get mixed up, because they're like, am I plugging this into f prime of x, or am I plugging it into f of x? If you plug those numbers back into f prime of x, what do you get? 0. That's not where you're going to go plug it, because we already know they're 0. So you're going to plug the critical numbers into f of x. And then you have to also check your endpoints. So I need to go check f of negative 1 and f of 2. So I'll give you a moment. Go plug negative 1 into f of x and go plug 2 into f of x and get your outputs. So now you look at these four options. The smallest one I see is negative 1. So there's a relative minimum at 1, negative 1, and the biggest one is 16. So there's a relative maximum at 2, 16. Okay? All right, questions on that? All right, let's do another one. In example 3, you want to find the extrema of f of x equals 2x minus 3x to the 2/3 on the interval, closed interval, negative 1 to 3. So go ahead and find the derivative first. Okay, now the problem is, in order to determine or figure this out, you need to actually build a fraction. And you need to build a fraction with a common denominator. Okay? Because, and you don't want to just subtract the 2 and then multiply by x to the 1/3, because then you're going to lose part of your critical number. Okay? So anytime you have a fraction, you need to build a common denominator to build one fraction. So watch what's going to happen. I'm going to multiply this second one by x to the 1/3 over x to the 1/3. So that's 2x to the 1/3 minus 2 over x to the 1/3. Now critical numbers can happen two ways. It's where the derivative is 0 or where the derivative is undefined. Well, where can you get something to be undefined? Where a denominator would equal 0. Ah, okay. So now I'm going to set the numerator equal to 0, because that'll tell me where the derivative is 0. So I can factor out the 2, or divide by the 2. So I'm getting x to the 1/3 equals 1, so x is 1, so that's a critical number. And then where is the denominator equal to 0? At 0. So my critical numbers are at 0 and 1. And then you're going to check the critical numbers and the endpoints. Don't forget the endpoints. So I get f of 0, f of 1, f of negative 1, and f of 3. Okay, so I'm going to give you a moment for you to calculate those. And you do need a calculator. You do get a little decimal thing here. Okay, so I'm getting a relative maximum at 0, 0, and a relative minimum at -1, -5. Now on closed intervals, they might also be the global, you know, they can be the same. So don't forget, to find critical numbers, it's where the first derivative is 0 or undefined. And this is where it gets tricky right here in this step, is 2x to the -1/3 is 2 over x to the 1/3. So it's a fraction, and you have to remember to build one fraction. All right, let's look at the last example. So this will be due on Monday. Find the extrema of f of x equals 2 sine x minus cosine 2x on the interval from 0 to 2 pi. All right, so find the first derivative. I'm going to give you a moment. You have to use the chain rule here.
Oh, I graded it as I just forgot to circle.
Oh, okay. Yeah, just make sure you do that. Oops, sorry, I'm throwing papers over here.
You got the note card.
Okay, so to do the derivative, you're getting 2 cosine x minus, now the derivative of cosine is negative sine 2x, but then you have to multiply by the derivative of the inside. Did you remember that? So this is going to be 0 equals 2 cosine x plus 2 sine 2x. You can put that 2x in a parenthesis if you'd like. Now, here's the problem. How on earth are you going to solve that equation? You're
Use
going,
your calculator.
no, you're not going to use your calculator.
If you just plug in 0, you can do it.
You have to find the critical numbers.
You can't plug in 0.
Ian?
You have to use a trig identity.
Okay, you need to use a trig identity here. You need to recall that the sine of 2x is equal to 2 sine x cosine x. And do you remember we've seen this like 4 times this year already? So this is one you need to commit to memory. This one's going to appear on your AP test. So let's use that trig identity. And we're going to replace sine 2x with 2 sine x cosine x. And then guess what? This is going to factor for us. So I have a GCF of 2 cosine x. This will be 1 plus 2 sine x. And then I'm going to use my 0 factor property that says I can set 2 cosine x equal to 0 or 1 plus 2 sine x equals 0. I'll divide by 2 over here. I'll subtract 1 and divide by 2. And I'm going to pause a moment and let you think about your unit circle. See if you guys can come up with it. Excuse me. Thank you. on this one.
Use the cosine. I got that one.
So cosine x equals 0. What's from 0 to 2
over
pi?
2 and 3 pi over 2.
Nope.
Just
Pi
kidding.
to 2 pi.
Or wait a minute. What'd you say? Yeah, it was pi over 2, 3 pi over 2.
Oh,
Sorry.
my dreams. They're big
Sorry,
fun.
no. I was thinking it was equal to 1. I'm like, no.
I didn't even use my calculator on that.
Yay.
I'm scarred.
Sorry. Alright, sorry about that. Alright, sine x equals negative 1/2. What's x there?
Sine in
That's
3
3 pi over 2. Okay, so now you need to try these three values plus the. Did I miss something?
Isn't it only two
The
values?
sine x thing wrong. Maybe.
Wait a minute, that isn't 3 pi over 2. Sorry.
Is this it?
I'm like, wait a minute. That's,
More complicated.
yeah.
5 pi over 6.
Yeah.
Just kidding, I don't know.
Something
It's
over 6.
7 pi over 6 and 11 pi over 6, right?
I have to review this.
Need to wear my t-shirt.
So we need to check f of pi over 2. Now you guys, you really should be able to do this without your calculators. So let me go through it nice and slowly with you. So that means everywhere you see x, you're going to replace it with pi over 2. So sine pi over 2 is 1. This ends up being the cosine of pi, which is negative 1. So that's 3. F of 3 pi over 2. Now you're going to f of x, remember? So this is 2 times the sine of 3 pi over 2 minus cosine 2 times 3 pi over 2. Sine of 3 pi over 2 is negative 1.
So we do this 4 times.
Isn't that 0?
We have to do
No.
it 6 times.
The 3 pi
Oh, yeah, good
is equal to pi.
What?
So it's a
Just
negative
do
negative 1.
Yeah, I don't have to do any of them.
So negative 2 plus 1 is
Negative 1.
negative 1.
Fingers.
I'm not listening. So I'm doing f of 7 pi over 6, which would be 2 times the sine 7 pi over 6 minus cosine 2 times 7 pi over 6. Well, 7 pi over 6 is negative 1/2. So that's the cosine of 7 pi over 3.
Ew.
Alright,
Oh,
well,
we're done.
2 pi over 3 is 6 pi over 3, right? So this is just into the first quadrant, so that's 1/2. So isn't that negative 3/2?
Yeah.
And then f of 11 pi over 6 is 2 times the sine of 11 pi over 6 minus the cosine of 2 times 11 pi over 6. That's 2 times negative 1/2. Okay, 11 pi over 6.
Is equal.
I mean, 11 pi over 3.
Two,
well,
2 pi over.
It's almost a 12, right?
Yes, it's 2 pi. No.
No.
It's not 2 pi over 3.
No.
It's 5 pi over 3.
6 pi over 3 is twice. 5, yeah, it's the fourth quadrant. So that's a positive 1/2.
How did you not know that?
So I'm getting negative 3/2 again. And now we have f of 0. That's 2 sine 0 minus cosine 0.
Equals 0.
That's 0 minus 1. And then f of 2 pi is the sine 2 pi minus cosine 2 times 2 pi is 4 pi.
Could it possibly be
So
8
also
pi?
there's 2 pi.
So that's negative 1.
They're literally screaming out in the hallway. I don't understand.
Yeah, I know.
So there's 2 relative. whatever.
Yeah, so we're going to have, what's the relative max?
78.
Pi over 2.
Pi over 2. So there's a relative max
That was close.
at pi over 2 comma 3. And then negative 3/2 is smaller than negative 1, right? So we have two relative minimums. So we have relative minimums at 7 pi over 6 comma negative 3/2 and 11 pi over 6 comma negative 3/2. Did you notice I gave you a whole lot of space on that page? That was not an accident. That was intentional. Okay, that finishes the notes. It sounds like, though, maybe I need to create a solve trig equations
I just
for review.
forget my
Okay, let me return the test, you guys. I was so impressed. However, I flubbed up on 2 of the problems.
Yeah, I mean, darn it.
Oh, look, I got a 63.